In this chapter we shall study laws that govern thermal energy. We shall study the processes where work is converted into heat and vice versa. Thermodynamics is the branch of physics that deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. Thermodynamics is a macroscopic science. It deals with bulk systems and does not go into the molecular constitution of matter. Thermodynamic equilibrium. The state of a system is in thermodynamic equilibrium state if the macroscopic variables that characterize the system do not change in time. For example, a gas inside a closed rigid container, completely insulated from its surroundings, with fixed values of pressure, volume, temperature, mass and composition, that do not change with time, is in a state of thermodynamic equilibrium. Zeroth law of thermodynamics. Two systems in thermal equilibrium, with a third system separately, are in thermal equilibrium with each other. First law of thermodynamics is simply a restatement of principle of conservation of energy. Imagine a gaseous system, for which pressure P, volume V and temperature T are related by certain equation of state, and is undertaken through a process. If delta Q, delta U and W represent the heat given to the system, change in internal energy, and work done by the system respectively. During the process, the first law of thermodynamics states that heat given to the system is equal to the sum of work done by the gas and change in its internal energy. That is, delta Q is equal to delta U plus W. We have learned how to calculate work done by a force. It is mathematically expressed as integration of dot product of F vector and dl vector. For mathematical simplicity, let us consider a cylindrical vessel of cross-sectional area, A, which is filled with certain gas, enclosed by means of a movable piston. For an infinitesimal displacement dl of the piston, the gaseous pressure, P, can be taken as constant. Hence during the displacement dl the force exerted by gas on piston equals Pa. Hence the work done in displacement dl equals to P into A into dl. But A into dl is equal to dV. Hence dW equal to P into dV. In isochoric process, that is constant volume process, change in volume is zero. Hence no work is done in an isochoric process. However, in constant pressure process, that is, isobaric process, work done is equal to product of pressure and change in volume. If volume of gas increases, that is when gas expands, work done by gas is positive, whereas during compression work done by gas is negative. In an isothermal process, during which temperature of system remain constant, work done is given by nRT log V2 by V1. It can be derived mathematically, as shown. In an adiabatic process, the system is insulated from the surroundings, and heat absorbed or released is zero. We know that work done by the gas results in decrease in its internal energy, and hence its temperature for an ideal gas. For an adiabatic process, of an ideal gas, PV to the power gamma is constant, where gamma is ratio of Cp to Cv. The expression for work done in the process is as represented in the show. Molar specific heat capacity is defined as amount of heat required to increase temperature of 1 mole of substance by unity. It is independent of the amount of substance. It depends on the nature of the substance, its temperature and the conditions under which heat is supplied. Its unit is joule per mole per Kelvin. As already remarked, the specific heat capacity depends on the process, or the conditions, under which heat capacity transfer takes place. For gases, the value of specific heat capacity ranges from 0 for adiabatic process to infinity for an isothermal process. It can even be negative. Two main specific heats are specific heat capacity at constant volume and specific heat capacity at constant pressure. For an ideal gas, we have simple relation, Cp minus Cv is equal to R, where Cp and Cv are molar specific heat capacities of an ideal gas at constant pressure and volume respectively, and R is the universal gas constant. This relation is known as Mayer's relation and can easily be established as represented. Heat engine is a device by which a system is made to undergo a cyclic process that results in conversion of heat to work. It consists of a working substance, the system. For example, a mixture of fuel vapor and air in a gasoline, or diesel engine, or steam in a steam engine, are the working substances. The working substance goes through a cycle consisting of several processes. In some of these processes, it absorbs a total amount of heat QH from an external reservoir at some high temperature TH. In some other processes of the cycle, the working substance releases a total amount of heat QC to an external reservoir at some lower temperature TC. The work done, W, by the system in a cycle is transferred to the environment via some arrangement. For example, the working substance may be in a cylinder with a moving piston that transfers mechanical energy to the wheels of a vehicle via a shaft. The basic features of a heat engine are schematically represented in figure. The efficiency of a heat engine is defined by work done per unit heat input. A refrigerator is the reverse of a heat engine. Here the working substance extracts heat Q2 from the cold reservoir. At temperature T2, some external work W is done on it, and heat Q1 is released to the hot reservoir at temperature T1. In a refrigerator, the working substance, usually in gaseous form, goes through the following steps. First, sudden expansion of the gas from high to low pressure, which cools it and converts it into a vapor-liquid mixture. Second, absorption by the cold fluid of heat from the region to be cooled, converting it into vapor. Third, heating up of the vapor due to external work done on the system. And finally, release of heat by the vapor to the surroundings, bringing it to the initial state and completing the cycle. The coefficient of performance of a refrigerator is given by ratio of heat extracted from the cold reservoir to work done on the system. A heat pump is the same as a refrigerator. What term we use depends on the purpose of the device. If the purpose is to cool a portion of space, like the inside of a chamber, and higher temperature reservoir is surrounding, we call the device a refrigerator. If the idea is to pump heat into a portion of space, the room in a building when the outside environment is cold, the device is called a heat pump. The coefficient of performance of a heat pump is given by ratio of heat given to hot reservoir to work done on the system. The first law of thermodynamics is the principle of conservation of energy. Common experience shows that there are many conceivable processes that are perfectly allowed by the first law, and yet are never observed. For example, nobody has ever seen a book lying on a table jumping to a height by itself. But such a thing would be possible if the principle of conservation of energy were the only restriction. The table could cool spontaneously, converting some of its internal energy into an equal amount of mechanical energy of the book, which would then hop to a height with potential energy equal to the mechanical energy it acquired. But this never happens. Clearly, some additional, basic principle of nature forbids the above, even though it satisfies the energy conservation principle. This principle, which disallows many phenomena consistent with the first law of thermodynamics, is known as the second law of thermodynamics. The second law of thermodynamics gives a fundamental limitation to the efficiency of a heat engine and the coefficient of performance of a refrigerator. In simple terms, it says that efficiency of a heat engine can never be unity. For a refrigerator, the second law says that the coefficient of performance can never be infinite. This implies that external work can never be zero. The following two statements, one due to Kelvin and Planck, denying the possibility of a perfect heat engine, and another due to Clausius, denying the possibility of a perfect refrigerator or heat pump, are a concise summary of these observations.